Hello, and welcome back to the course on thermodynamics. So in this lesson, we will now be ready to find the first law on thermodynamics. But before that, let us first review some lessons. So in the previous lessons, we have discussed about what is a thermodynamic system and how does the path between thermodynamic processes affect the heat absorbed or released by the system and the work done or by the system. So in this lesson, we will first discuss what is the internal energy of a system and then define the first law of thermodynamics. So the internal energy of a thermodynamic system is designated by the letter U, and it's basically the sum of the kinetic energies of all the particles of the system plus the sum of all the potential energies of the interaction among these particles. So that's the internal energy, the kinetic plus potential energy of all the particles belonging to that system. So this system can actually absorb or release heat, and the system may also do work, or work may also be done on the system. And if that happens when it absorbs or releases heat, or it does work or work is done on it, its internal energy can change because of the exchange in energy. And the first law of thermodynamics states that the change in internal energy of a thermodynamic system is just the difference between the heat absorbed by the system and the work done by the system. So in terms of mathematical equation, it's this one. So the change in internal energy, this is final internal energy minus the initial internal energy, is just equal to the heat absorbed minus the work done by the system. So it's basically a generalization of the principle of conservation of energy. For an ideal gas, which is wherein most of the time we only consider the ideal gas, the change in internal energy, delta U, only depends on the change in temperature. So it's actually equivalent to N, the number of moles of gas, the heat capacity at constant volume, times the change in temperature. So again, this is only true for an ideal gas, and this is not true for everything else. For an ideal gas, the change in internal energy depends only on the change in temperature. So, going back to the first law of thermodynamics, uh, unlike heat and work, which depend on the path, uh, of the thermodynamic process, the change in internal energy does not depend on the path, but only on the initial and final states of the system. So it's something like a conservative quantity. So in the previous example, we have shown that the work in changing the state of the particle from state 1 to state 2, or in the thermodynamic process from state 1 to state 2, the work will actually depend uh, on the path, whether it's the path 132, the path 142, or the direct path 1 2. So the work will change depending on the path. But the change in internal energy of all of these paths are just the same. So all of these paths will result in the same change in internal energy, because the change in internal energy only depends on the initial state and the final state, and that doesn't matter on the path. So we can use the analogy of coffee. So the internal energy of a cup of coffee depends on its thermodynamic state. That is how much water and ground coffee it contains, and what is the temperature of this coffee. It does not depend on the history of how the coffee was prepared. That is the thermodynamic path that led to its current state. So that's just the analogy. So it only depends on the initial and the final states. So if you want to make coffee, uh, the initial state, for instance, you have water, you have ground coffee, and then you change its temperature, and then the final state is you now have a coffee. So the change in internal energy of the raw ingredients is just equal to the change in internal energy of the final product. So that's the analogy. So in this example, if there's more heat added to the system as compared to the work done by the system, then in that case, the internal energy of the system increases. So in this case, it absorbs 150 joules of heat and it only does 100 joules of work. Then the change in internal energy is Q minus the work, heat minus the work. So you get positive 50 joules. In this example, if more heat flows out of the system than the work done on the system, then the internal energy of the system will decrease. So in this case, there's negative work, meaning work is done on the system. And then there's negative heat, meaning heat is released by the system. So if you calculate the change in internal energy of that, Q is negative 150 minus negative 100, you will get negative 50 joules. So meaning the internal energy of the system decreases. In this example, the heat added to the system equals the work done by the system. And in this case, the internal energy of the system is unchanged. So this is an example of a cyclic process where the internal energy of the system, after a certain thermodynamic process, it just returns to its original state. So the change in internal energy is zero. So our body is a thermodynamic system. So when you exercise, you're actually doing positive work. But since you're also sweating, you're urinating, or say pooping in the middle of exercise, uh, your body is just releasing heat. So those are the ways your body can release heat: by urination, by sweat, or by pooping. So in this case, work by your body is positive. The heat release by your body is the heat uh, Q is negative because heat is released during exercise. So meaning the change in internal energy is will be negative. So if you exercise, the change in internal energy of your body will be negative, and that means uh, that's why exercise will help you lose weight, because you will decrease your internal energy. It uses some of the internal energy stored in your body in the form of fat. So some of the internal energy of the human body is stored in fat. And if you want to burn that fat, you need to exercise. So you need to do work, and you need to release some heat so that all of those fat will be burned. So a cyclic process, or a cyclic thermodynamic process, is a process that eventually returns the system to its initial states, as we have mentioned before. So meaning, in that case, the change in internal energy is zero because the initial and the final states are just the same. You return to the initial state. So this is an example of a cyclic process involving the human body. So you're sleeping for 8 hours, you're actually doing work. So even though you're sleeping, your body is actually doing work. Your body is actually burning energy. So when you eat your breakfast, you're actually both absorbing heat and doing work. So you're absorbing heat in the form of food, so chemically stored energy that will be converted into heat later in your body. And you're doing work because you're doing the motion, you're moving your body, you're moving your hands, you're moving your arms. But that's just a very small amount of work as compared to the amount of heat that you absorb. And then you do your work, morning work, and then you go to lunch again, you absorb a large amount of heat, you do some work, and then your afternoon work, and then dinner again, you eat some food, you absorb some heat, and you do some work. and then you exercise before you go to bed, and then you watch TV, and then you sleep for 8 hours again. And it's a cycle. If you add all of the heat absorbed by your bodies, it will be equal to, in this case, to 16.5 times 10 to the 6 joules. And if you add all of the work done by your body, it will also be equal to the same amount of uh, work as the heat. So in this case, the change in internal energy of your body is equal to 0. So meaning Q is equal to the work. The heat absorbed by your body is just equal to the work done by your body. So if you want to maintain your weight, you should undergo a cyclic process. So you should burn all of the heat absorbed by your body, all of the food absorbed by your body, and convert them into work. So that's a cyclic process. But again, if you want to reduce your weight, you should do a lot of more work as compared to the heat that you absorb if you want to do more work. But of course, the more common thing that happens is we absorb a lot amount of food or heat, we do a little work, and that's why you get fat or you increase your weight. So if you want to maintain your weight, do a cyclic thermodynamic process with your body. Now, as opposed to cyclic process, we also have an isolated system such as a calorimeter. So this is a system where no work or heat flows into or out of the system. So in this case, the change in internal energy is 0 because there's no work or heat, and there's no work or heat, meaning work and heat is just equal. They are all equal to 0. No heat flows into or out of the system. No work is done on or by the system. So that is what we call an isolated system. So all of the work and heat is equal to 0. So first example. So working off your dessert. So you propose to eat a 300 calorie hot fudge sundae with whipped cream and then run up several flights of stairs to work off the energy you have to take in. So you need to burn all of the hot fudge sundae calories that you have eaten. So the question is, how high do you have to climb? So what's the height of the building that you need to climb, assuming your mass is 60 kilograms? Okay, uh, I forgot to mention that in the unit for, or I think we have mentioned it before when we discuss about quantity of heat, that one food calorie, the capital C in calorie, that's actually a food calorie. When you encounter calories regarding food, that's actually a food calorie, and that's equivalent to 1,000 heat calories or 1,000 calories with a small letter C. So basically, a 300 food calorie is equivalent to 300,000 heat calories. So 300 food calorie, the capital C, is equivalent to 1,000 calories. So 300 calories means 300,000 heat calories. So you convert that into joules. One calorie is 4.186 joules, and you will get 1,255,800 joules. So that's the amount of heat that your body absorbs when you eat a 300 calorie hot fudge sundae. Okay, so in this case, we will assume that you will undergo a cyclic process, meaning all of the heat that you absorb will be converted into work. So in this case, the work done in climbing a flight of stairs is just equal to the potential energy at the top, assuming the potential energy at the ground is 0. So the change in the potential energy is just the potential energy at the top of the building, which is mg times y, the height of the building that you need to climb. So solving for y, knowing q, so y is just q over mass times g. So we now have q, we have the mass, g is just the acceleration due to gravity, 9.8 meters per second squared, and you get 2,135.7 meters. So this is actually a very high building. So assuming one-story building is 3 meters in height, then this is equivalent to 712-story building. So there are no 700 story buildings in the world. So this is not actually a final value because we have not taken into account how efficient the human body is in converting heat into work. So we will go back to this problem uh, in the next unit when we discuss about the second law of thermodynamics. So another example is the thermodynamics of boiling water. Okay, so you have 1 gram of water. So by the density of water, 1 gram per centimeter cube, meaning its volume is 1 centimeter cube. So 1 gram of water or 1 centimeter cube or 1 ml, 1 centimeter cube is 1 milliliters or 1 ml of water becomes 1,671 ml or centimeter cube of steam when boiled at a constant pressure of 1 atm. So the heat of vaporization of water at this pressure, so this is actually a constant, the latent heat of vaporization of water. So compute the work done by the water when it vaporizes and its increase in internal energy. So for letter A, work done. So it's just the pressure times the change in volume, V2 minus V1. So V2 is 1,671 ml or centimeter cube. V1 is 1 centimeter cube. The pressure is 1 atm. Of course, we need to convert that into standard units. So 1 atm is 1.013 times 10 to the 5 pascals. And 1 million centimeter cube is equivalent to 1 cubic meter. So 1 million ml, that's 1 cubic meters. So the centimeter cube unit will cancel and you will get the meter cube times pascal, sorry, and that will give you a unit called joules. So in this case, the work done by the water in expanding. So again, this is an expansion. So you expect a positive work because this is a positive change in volume. So you have a positive work of 169.17 joules in expanding from 1 centimeter cube to 1,671 centimeter cube. Now for letter B, we're asked to find the change in internal energy. So before we can solve for the change in internal energy, since change in internal energy is just Q minus W, heat minus the work, we know the work, but we still don't know the heat absorbed by the water. So the heat absorbed by the water during an evaporation process is just equivalent to the mass of the water times the latent heat of vaporization of water. So it's just the mass of water, 1 gram, 0.001 kilogram, convert that into kilogram, and the latent heat of vaporization, joules per kilogram, and then you will get an answer in joules, 2,256 joules. So 1 gram of water absorbs 2,256 joules to become 1,671 centimeter cube of steam. So we can now solve for the change in internal energy of the water. So it's just Q minus the work. So we now have Q. We have solved the work in the previous problem, and we get 2,086.83 joules. So in this case, the internal energy of the water, the boiling water, actually increases by 2,000 or more than 2,000 joules. So for our last example, this is a combination of the lesson in the in Unit 2, the ideal gas, and the focus of the lesson in Unit 3, which is the first law of thermodynamics. So suppose you have 5 moles of ideal monoatomic gas with an initial temperature of 127 degrees Celsius. And this gas expands and in the process absorbs 1,200 joules of heat and thus 2,100 joules of work. So what is the final temperature of the gas? So for an ideal gas, the change in internal energy only depends on the change in temperature, as I have mentioned before. Again, this is only true for an ideal gas. The change in internal energy is equal to this only for an ideal gas and not for anything else. So the change in internal energy is Q minus the work. It's equal to this one. So we know the heat absorbed by the gas. It's 1,200 joules. We know the work done by the gas. It's 2,100 joules. We know the number of moles. It's 5 moles. CV, the heat capacity at constant volume, is just equal to 3 halves R. If you have an ideal monatomic gas, so that's approximately 12.47 or 12.5 joules per mole Kelvin. We have the initial temperature. it's 127 degrees Celsius. So of course, you need to convert that into Kelvin. It's around 400 Kelvin. The only unknown is here, is this term here, the final temperature T. So you solve for T, you will get this one. Substitute all of the values. So the initial temperature is 127 degrees Celsius. Convert that into Kelvin. That's actually 400 Kelvin. And then you will get an answer of 385.71 Kelvin. If you are required to get the temperature in degrees Celsius, so you subtract 273 from this, and you will get 112.56 degrees Celsius. So we now have a problem which combines the topics in Unit 2 and Unit number 3. So that's all. So that is it for the fourth lesson of this course, which is all about the first law of thermodynamics. Now, in the next lessons, we will now discuss the different kinds of thermodynamic processes and what happens to the first law of thermodynamics under these processes. So I will see you again in the next lesson.